Mm, okay, I think we're good. So, hello everyone, and welcome to this junior researcher webinar. Thank you for being here. Today we'll be listening to Emmanuel REY-HERME, who is a postdoc at LP2I-Bordeaux, and he will present the result of his PhD on pear-shaped nuclei in the actinides, the decay spectroscopy of protactinium 2025.
Hello, everyone. First, thank you for being here, listening to this. So indeed, I'm going to present a little bit what I did during my PhD thesis on the study of the pear-shaped nuclei in the actinides, and with the specific case of protactinium-225. And for that, first, I need to present a little bit about octupole collectivity. Octupole collective, so first I will present a little bit about octupole collectivity, then I will present the I262 experiment, which is the experiment I analyzed during my thesis, and then the season detector on which we were working at IRFU. So for the octupole collectivity, it is something that is occurring on the nuclear chart at several places, and there are kind of magic numbers, specific numbers for octupole collectivity that occurs right above closed shells. And there are two main regions. The first one is TIS1 around barium 124. And this region have been studied a lot using Coulomb excitation experiments to determine the deformation of the nuclei in this region. And the other region, the one we would be interested here, is this one of the neutron-deficient actinides. It is a region centered around radium-224, more or less. And there is a few cases of study through Coulomb excitation with the most known one, radon-220 and radium-224. But there is also predictions for more octupole deformations. There is a lot of different theoretical models that agrees to predict deformation in this area. You have the example of one calculation here with proton number, neutron number, and the color scale is the variation of energy of the ground state when one allows for octupole deformations in the calculations compared to the case with only quadrupole deformation. And one can see that the impact on the energy of the ground state, the stabilization, can be of more than 1 MeV in the calculations for some nuclei. However, so there is a large area that is predicted to have deformation, but only a few experimental measurements. And this is because Coulomb excitation in this region is not accessible for most of the neutron-deficient actinide, or at least hard to do. So we need to find other signatures. And to discuss those other signatures, we need to think a little bit about the impact of quadrupole collectivity. And there are two things. First, there is a removal of the single particle orbital degeneracy. This is what is called Nielsen diagrams. So if we go back to the shell models, you have an example of a few levels in the shell model here, and the degeneracy indicated here when there is deformation is removed, as since with deformation there is a symmetry axis that appears, there is new quantum numbers that can be defined, and the degeneracy is removed. And if we look here, this is a Nielsen diagram. We have the deformation, the quadrupole deformation on the axis, and the energy of the states in the y-axis. And so for zero deformation, we find back the shell model, the same orbital as here. And when the deformation increases on one or the other side, the orbitals split into several different orbitals that have a new way of numbering. And one of the most important quantum number here would be omega, which is the projection of the total angular momentum on the symmetry axis, and which is often also associated with K. The second behavior appearing is rotational and vibrational, but we will mainly speak about rotational behaviors. When you have a rotational behavior, if you take one of these orbitals here, you can have, so you have a state associated with it, and on this state you will have a rotational band that is built. This is in the general cases. In specific cases, especially if this is a 0+ state, you will only have even levels, even spin levels. But in the general case, you can have all, and we will mainly speak here about odd mass cases where it behaves like this. And if we go to an excited state, you can have a second K1 with parity pi, and on this K1, you can build also a rotational band. Now, if we go to octupole conductivity, we keep in mind what happens to quadrupole deformation, and we take an ideal case of what we will call perfectly rigid octupole deformations. This means that if we plot the potential as a function of the octupole deformation here, beta 3, you have a minimum of potential energy for non-zero deformation, and you have an infinite potential barrier at 0. In these ideal cases, in the intrinsic frame of the nuclei, the parity is not a good quantum number anymore, since the states with same spin but opposite parity will be mixed. This arises due to the breaking of the reflection symmetry in this pear shape. And so your rotational band will be the same, except that the parity of the levels will not be well defined, or to say that otherwise, the state will have both positive and negative parity. Now, this is an ideal case, and in reality, the potential barrier here will never be infinite. And this has an effect to split the two parity levels here. And we don't have anymore one band, but we have two bands of opposite parity, but same band heads and same progression here. And typically the splittings between the two band heads here for odd mass nuclei in the actinide, it will be of the order of a few tenths of keV. And then one can consider the case of octupole vibration, where the minima is now for 0 deformation, but vibration around this 0 deformation are allowed. This means that the ground state does not have octupole deformation anymore, but excited states incorporates a part of octupole behavior. And in this case, you will have the same structure, but the energy splitting will increase, and typically it will be of a few hundreds of keV. And here we have a first signature in level scheme of octupole deformation, which is the presence of parity-doublets. The second signature we will need here, we will find it in alpha decay. Indeed, in the actinide, it's a region where the main decay mode is alpha decay. And one can modelize alpha decay through a barrier tunneling model, which was initially the Gamow model. One assumes that an alpha particle is already existing, preformed inside the nucleus, and that this alpha particle bounces off the potential barrier of the nucleus, the Coulomb barrier. And each time it bounces off this barrier, it has a certain probability of passing through the potential barrier and then escaping the nuclei, and this is alpha decay occurring. So with that, one could compute a theoretical half-life for the alpha decay, combining the assault frequency and the tunneling probability. But this pictures is missing structure effects. One makes the assumption that the nuclei is already the alpha particle is already preformed in the nuclei, already existing and not taking into account how hard it would be to produce this alpha particle inside the nuclei. And a measurement of the structure effect will then be the hindrance factor, which is the ratio between the experimentally measured half-life and the theoretically computed one. So this hindrance factor is an empirical measurement of the impact of structure effects on alpha decay. And if there is a very low hindrance factor, this means typically between 1 and 4, it means that the initial and final single particle states in the alpha decay are identical or almost identical. And as the hindrance factor increases, it means that the initial and final states wave function are more and more different. Producing this alpha particle means changing a lot the wave function. And one thing that is notable is that alpha decay tends to conserve parity, and thus a parity change will produce large hindrance factor. By large, I mean typically above 100. However, in the case of octupole deformation, as I said, parity is not a good quantum number anymore. There is a mixing of opposite parity states. And thus, in the case of octupole deformation, alpha decay toward opposite parity states becomes more favored than in the case without octupole deformation. And the hindrance factor in these cases will be typically around 10 for a transition that change parity. So here we have a second signature of this octupole collectivity in the change of parity, in a transition changing the parity with low hindrance factors. So as a summary for this part, we have octupole deformation predicted in the neutron-deficient actinides. The study through Coulomb excitation, the usual method for octupole deformation, is hard or impossible. And we have two signatures of octupole deformation for this work: the presence of parity-doublet and the low hindrance factor toward opposite parity states. Now, for the I262 experiment, it's an experiment that took place in July 2020 in IGISOL, Ion Guide Isotope Separation On-Line at Jyväskylä. So this is the scheme of the IGISOL installation. And we had a thorium-232 target here in the target chamber, on which was impinging a proton beam at 65 MeV. And this was, we were making a fusion-evaporation reaction with the evaporation of a few neutrons and a few protons in some cases. And with that, we were producing the neutron-deficient actinides. And then right after the target, which was a very thin target, we had a gas cell to stop the ions produced. And the ions were then extracted from the gas cell and guided here toward a dipole magnet where mass selection was performed. And during the experiment, we had range from mass 218 to mass 227. And then the ions are guided toward a spectroscopy line where a decay spectroscopy setup was installed for alpha, gamma, and conversion electron decay spectroscopy. So this is a scheme of the setup. So we have the proton beam here impinging on the target. The gas cell is here. It was extracted, guided here, mass separated, and then implanted in a carbon foil. Very thin carbon foil, typically 100 nanometers of thickness. And around this carbon foil, we had silicon detectors here to measure the alpha particle. And one of them, the silicon lithium detector, had also good enough performances to measure the conversion electrons at the same time. And we also had germanium detectors around the setup to measure the gamma rays in coincidence. So this is a summary of what was produced during the experiment. So we had our beam on target of thorium-232, and we are producing from protactinium-233 to protactinium-225 here on the protactinium line, and also lower lying isotopes. And my data analysis focused on the alpha decay of protactinium-225 toward actinium-221 and then toward francium-217. And when the experiment was performed, the literature for this decay of proton-225 could be summarized in this table, with only 3 alpha lines known and no gamma rays or conversion electrons ever measured in coincidence. So for the data analysis, we have first a step of reconstruction of the events, energy calibrations, efficiency calibrations, then extraction of the alpha peaks, energies and intensities. And for that, we need first to properly identify all the peaks. You have here the example of the energy spectrum measured in the CD. So this is the energy measured in the CD, the number of counts, and each peak signals an alpha ray. And we had 5 decay chains that were present in the experiment. The first 2 are the blue and the red one for thorium-225 and protactinium-225, which were the nuclei of interest produced in this run. Then we had also a little bit of contamination coming from the mass right above due to a tail in the mass distribution. And so we have thorium-226 and protactinium-226. And we also have radium-224, which is coming from previous decay, previous run, sorry, that had a long half-life of a few days. So all of the peaks in T spectrum are identified and then fitted with deformed Gaussian. And with that, we managed to fit the whole spectrum at once without using any background, only using deformed Gaussians for each peak. Then, once this identification is done, we worked with alpha-gamma matrices. So we have the energy of the alpha particle here, the energy of the gamma ray measured in coincidence here with the time window, in the time coincidence window of 1 microsecond. And on this 2D matrices, we can plot this line, which corresponds to this equation here, which is basically the idea that if you have an alpha decay toward an excited state, and then this excited state goes directly, emits a gamma ray going directly to the ground state, the sum of the energy liberated during the alpha decay and the energy of the gamma ray is always the same. It's the energy difference between the 2 ground states. So the spots, the coincidence falling on this line are coincidences in which the gamma rays goes directly to the ground state, and thus it enables the reconstruction of the level scheme. It enables the identification of the levels. So here you have the examples of the levels identifications. And then if we take one of those energies, and if we look at gamma ray corresponding to the same alpha particle energy, we can find other peaks. And with that, we reconstruct also the gamma rays going from an excited state to another excited state. And with that, we are able to reconstruct the level scheme of actinium-221. Which is represented here. So we have the energy of the alpha particles, the intensities, the hindrance factors toward those states, and then all the states and all the gamma rays linking them. And in addition, since we had a measurement of conversion electrons, even though there was a few technical difficulties that I will not detail here, we were able to measure to reconstruct the conversion coefficients for the electrons. And with that, you reconstruct the multipolarity of each of those transitions. And in turn, we are able to reconstruct the spin and parities of the levels. With that, we can move to the interpretation, and we will reorganize the levels into 2 bands, and it gives that. So this is exactly the same thing. We have the same levels, all the gamma rays between them, but they are splitted in 2 bands. And in the black boxes are indicated the hindrance factors for the alpha decay toward those states. And if we look a little bit at the literature, at the surrounding literature, we can find that actinium-223 has a very similar structure. First, the first thing we can notice is a very low hindrance factor towards the ground state into the both case 2.5 and 2.9. In both cases, it's the lowest hindrance factor. And this is significant because typically the lowest hindrance factor is not for a transition toward the ground state, but toward an excited state that is arising from the same orbital as the ground state of the parent nuclei. However, here this can be understood using Nielsen diagram. So you have an example of a Nielsen diagram, the Nielsen diagram here with a quadrupole deformation here, but it is computed with a fixed octupole deformation. And with this fixed octupole deformation, the orbitals are not the same. And for our nuclei here, we have Z equal 89 and 9 for actinium and 91 for protactinium. So the two relevant orbitals here will be those two orbitals. So if we imagine we have a fixed deformation like this, the main orbitals would be here with one proton on the 3½ orbitals for the actinium isotopes, and 2 protons on the 3½ and 1 proton on the 5½ for the protactinium isotopes. However, this would mean that the ground state of actinium-221 would be a 3½ orbitals and would not be the same as for protactinium isotopes. But the actinium isotopes are predicted to have lower deformation, lower quadrupole deformation than their protactinium parent nuclei. And thus the deformation of actinium 221 and 223 would be more around here. And the ground state would then be also the 5½ because of this orbital crossing here. A second thing that is similar in both level scheme is the presence of low hindrance factor toward positive parity states, whereas the ground state of the parent nuclei is a negative parity state, hindrance factor around 10. And this was one of the signatures of octupole collectivity that we mentioned at the beginning. And we also have the other signature with the presence of parity-doublet with these 5½ minus 5½ plus states in both cases. However, here, if we look at the splitting, so we conclude to static octupole deformation, but if we look at the splitting between the two states, here we have 65 keV, which is right what we would expect, exactly what we would expect for a static deformation. But for actinium-221, we have 150 keV, which is larger than what is typically accepted for static octupole deformation, but lower than what is typically expected for octupole vibration. And we take that as a hint for a transition towards the octupole vibration region for more neutron-deficient actinium isotopes, especially since this is very consistent with results published in 2019 with a comparison between experimental laser spectroscopy measurement and theoretical computations. I won't show the experimental results, but they indicate that the theoretical calculation that managed to reproduce the best the experimental data is the one that include octupole deformation. And here you have the result of the deformation predicted, quadrupole and octupole deformation predicted with the different models. And the SLY 5S1, which is the only one including octupole deformation here, is the only one reproducing correctly the data. And actinium-221 is placed right here at n equal 132. So we see that we are still in the region of octupole deformation, but we are really at the limits between this region of deformation and the region without static deformation, but only octupole vibrational behavior. And all this analysis and interpretation was published in July 2023 in PRC. So as a summary, during this experiment, we had the production of neutron-deficient actinide at IGISOL, which enabled to perform alpha, gamma, and electron decay spectroscopy of protactinium-225 with a signature of static octupole deformation in actinium-221 and indication of a transition toward octupole vibration for more neutron-deficient actinide isotopes. However, in this experiment, we had a lack of detection efficiencies, especially for conversion electron, where the detection efficiency was roughly 1%. This means that the reconstruction of the conversion coefficient and thus of the multipolarities was far from easy. And that also we have signs that we are probably missing a state that we cannot see with the statistic we have, but that should be present to explain some of the behavior, some of the intensities. So we need to go to our setups with higher detection efficiencies, and this is what SEASON will be. SEASON stands for Spectroscopy Electron Alpha in Silicon Box Counter. It is a detector that is developed internally at IRFU, at CEA. And it has two goals. First, it is designed to act as a counting detector for laser ionization spectroscopy of heavy and super heavy nuclei. Just a few words on this laser ionization spectroscopy technique. The idea is to look at the atomic structure, the atomic hyperfine structure using lasers, a scheme of lasers to perform excitation and then ionization. And with that, one can scan the hyperfine structure by looking at the first laser frequency as at the number of counts as a function of the first laser frequency. And this hyperfine structure arises from correlation between the nucleus and the electrons, the atomic electrons. And thus the ground state, it holds information on the ground state properties of the nucleus, among which the mean square charge radii, the spin, the electric quadrupole moment, and the magnetic dipole moment. So SEASON wants to act as a counting detector for laser ionization spectroscopy and at the same time to perform alpha, gamma, and conversion electrons decay spectroscopy, and all of that at the low energy branch at S-cube. The idea is that the beams from S-cube will arrive from here, will be stopped in a gas cell, neutralized, and then extracted, formed into a gas jet in which laser ionization spectroscopy will be performed, and then guided here up to the SEASON detector, which will count the ions through the decay products. And there is also a mass measurement MRTOF-MS device to also perform measurement, especially in the case of longer-lived isotopes or cases that cannot be done with SEASON. So for that, if we take a closer look at the detector, we have the laser ionized atoms arriving here inside the main station, which is composed of 5 silicon detectors. I will come back to that later. And the ions are implanted on one of 11 implantation foils. And those implantation foils are mounted on a wheel so that when the laser frequency changes, the wheel can rotate and the foil that was initially here in the main station will be moved there into a secondary station. And in the main station, there will be a new foil free of contamination from the previous laser frequency. And then we have 2 germanium detectors, exogram detectors that will be placed behind the 2 stations to measure the gamma rays in coincidence. So if we take a closer look at the main station here, so we have 5 silicon detectors. Those are double-sided silicon strip detectors, 1 millimeter thick, to be able to stop conversion electrons up to 600 keV. And the distance between the detectors and the implantation foil will be variable in order to mitigate the case of larger count rates and not having summing effect or not blinding the detectors due to large count rates. And during my PhD thesis, I tried to make simulation as precise as possible of this detector, with inclusion of the proper detector model that will be used for season, inclusion of fine details such as the inactive border or the interstrip in the simulations. And also I studied the effect of the detection efficiency as a function of those variable distances. And we can have a look here at the efficiency as a function of both distances, one in the x-axis here and the other one as different color curves. And the nominal configuration will be this one here with a little bit more than 80% detection efficiency for the alpha particle. For comparison, during the I262 experiment, we had roughly 25 to 30% detection efficiency for the alpha particle. And we reach a better than 50% detection efficiency for the electrons in all cases, even taking into account summing effects that can occur due to series of transition emitting several conversion electrons at the same time. So on this part, I performed simulations of the setup using both Gen4 and NP tool, and we reach a better than 80% alpha particle detection efficiency and better than 50% electron detection efficiency. And I did not detail it, but I made a study of conversion electron summing. And I also performed a comparative study of carbon and silicon nitride foils for the implantation foils. And this led to the choice of the use of carbon foil for season. And those foils were used in October 2022 in an experiment at IGISOL, where we performed a similar experiment as the I262. And we used those carbon foils, implantation foils, mounted on a ladder, and the foil behaved very well. So as a conclusion, with the I262 experiment, we have a signature of octupole deformation in actinium-221 and hints of a transition toward octupole vibration region for more neutron-deficient actinium isotopes. But we also have evidence of the limitation of the setup, and for that we have new detectors coming, especially the season detector, with detailed simulations of the setup, choice of the implantation foil, and future experiment coming for season. Season's commissioning will occur. This is not right anymore. This should be fall 2024, using a proton and thorium reaction, fusion-evaporation reaction. So the same one as for the I262 experiment. But we have also other potential experiments to be performed at IGISOL using various beam target combination, using proton but also alpha beams, and using uranium, thorium targets to produce a variety of neutron-deficient actinides. And there is also a possibility for trap-assisted spectroscopy using GFL trap, which is a double penning trap, and putting the season detector behind to combine the purification of the traps with the decay spectroscopy performed by season. And then season will be installed at S-Cube Lab to combine decay spectroscopy and laser spectroscopy, but also to take advantage of the beam of S-Cube to study even more exotic nuclei, because with the reaction used at IGISOL, we are confined to nuclei quite close to stability. And then just a last word to say thank you to all the people I have the luck to work with and all the experiments I could take place in. And thank you for your attention. And if you have any questions, they are welcome.